So here's the video lecture on the central limit theorem. This is a very important topic to study. In particular, we will use it a lot in the second half of the course. So for a lot of what we do in inferential statistics, this is the theoretical foundation. So if you recall, we talked about random variables before, and we said that a random variable is a variable that the value changes based on the particular sample we take. And every random variable has a distribution, a mean, and a standard deviation. Now recall that x bar depends on the particular sample we take. So if we take a different sample, each different sample we get a different sample mean. Therefore, it's a random variable. So that means x bar itself has a distribution, and that distribution is called the sampling distribution of x bar. An x bar has a mean, and an x bar has a standard deviation. And the central limit theorem is what tells us the distribution, mean, and standard deviation of the sample mean. So if we're going to take a sample of size n from any distribution that has a mean mu and a standard deviation sigma, and the sample mean x bar may take on a whole range of values, some more likely than others. The mean of the distribution of x bar is denoted as mu sub x bar, which from the original sample it was denoted just mu. The standard deviation of the distribution of x bar is denoted sigma sub x bar. And now on what the central limit theorem says. It says that the mean of the distribution x bar is the same as the population mean. And this shouldn't be a surprise because if you take a sample mean, you expect it to be pretty close to the population mean. The standard deviation of x bar is not quite the same as sigma. It's a little bit smaller. So think of it this way. If you got a distribution of individual values, that's going to be more spread out than the distribution of a bunch of sample means. Because every time you take a sample mean, it pulls in those extreme values, those outliers. So the distribution of a bunch of middle values is not going to be as spread out as the original distribution of values. And it's smaller by a factor of square root of n. So if asked to find sigma sub x bar, you just need to find sigma and divide it by the square root of the sample size. And the last thing it says is we also know that x bar follows approximately normal distribution as long as one or both of these are true. First, we either need the sample size to be large. By large, we mean 30. That's usually the cutoff. So if the sample size is greater than or equal to 30, we consider it to be a large sample. Thus follows a normal distribution. Alternatively, if we don't know the sample size is large, but we still know that the original population being sampled follows a normal distribution, we can still say that it follows an approximately normal distribution, which in case you would be told in our circumstances that the original population follows a normal distribution. So in summary, the original population being sampled has a mean of mu, standard deviation of sigma, and it might follow a normal distribution, but it might not. And we have n items being sampled from this distribution. Now, if we are looking at the distribution of x bar, in other words, the sampling distribution, that has a mean of mu sub x bar, which is the same value of mu. It has a standard deviation of sigma sub x bar, which is equal to this sigma over square root of n, and it follows a normal distribution as long as either the sample size is large and or the population being sampled follows a normal distribution. So for those problems that we know x bar follows a normal distribution, we can use the normal distribution to find probabilities associated with x bar. So for example, if we suppose, like we did in the previous lesson, Suppose the high temperatures in June follows a normal distribution with a mean of 80 degrees and a standard deviation of 4 degrees. And suppose we randomly sample 20 days in June from the last 50 years. Does the sample mean follow a normal distribution? Yes, because even though the sample is only 20 days, which is a small sample, we are given that the original population is normally distributed. So we can still use the normal distribution for X bar. So what would be the mean and standard deviation of X bar? So we know that mu sub X bar would be mu from the original population, which is 80, and sigma sub X bar equals sigma, which is 4, over square root of sample size, which is 20. So we have 0.8944. So we can use this to find a probability. Now, if we wanted to find a probability that the mean of the sample of 20 that we took is between 78 degrees and 82 degrees, in other words, the probability that 78 is less than X bar is less than 82, we need to recall the last lesson that we need to convert x's to z's. So we use, but instead of x's, we need to convert x bar to z's. So we use the same formula as last time as converting x's to z's, but instead we use x bar. So we use now the mean of x bar and the standard deviation of x bar instead of the original population, mu and sigma. So to convert 78 and 82 to z for this problem, we have first 78 minus the mu sub x bar, which is 80, and then the standard sigma sub x bar, which we just found to be 0.8944. We get negative 2.24. And then again, for 82, we have 82 minus 80, and then over sigma sub x bar, which is 2.24. And now, if you look at the z table to get the probability of these numbers, you would look up first the probability of z being less than 2.24, like we do before, and we get 0.9875, but then we have to subtract the area below negative 2.24, and we get 0.0125, and that gives us 0.975, our probability. So that tells us there would be a probability of 0.975 that a sample of 20 from that population will be between 78 degrees and 82 degrees. If we look at another example, suppose we are looking at a large school and we have the mean number of people who withdraw from an Intro to Stats course is 18 with a standard deviation of 4.2, and we take a sample of 36 classes, and we want to find the probability that a random sample of 36 classes gets a sample mean of more than 20. In other words, that we want to find the probability that x bar is greater than 20. So the first question we want to ask is, does x bar follow a normal distribution? Well, in this problem, we have not been told that the population follows a normal distribution. That means that we have to look at the sample size. But as long as our sample size is greater than 30, and it's 36, and that's large, our sample then follows a normal distribution. Now again, what are the mean and standard deviations of x bar? We know that mu sub x bar is the same as mu of our original population, which is given to be 18, and sigma sub x bar is sigma of the original population, which is 4.2, over the square root of the sample size, which is 36, and that gives us 0.7. So now we want to find the probability that x bar is greater than 20. We need to convert first x bars to z's. So we take 20 minus 18, because this is mu sub x bar, and this is sigma sub x bar, which we just found, and we get 2.86. So if we look at the z table, the area to the left is 0.9979. So to get the area to the right, we get 1 minus 0.9979, which equals 0.0021. So would this be unusual? Well, if we recall the rare event rule, that any probability that is less than 0.05 is considered rare or unusual. Well, in our case, our probability is 0.0021. Therefore, yes, this probability is very small and would be unusual. So that concludes this lecture. Go to the example videos, and I'm posting one on central limit theorem.